Good morning or good afternoon, Physics 2 class. Today's going to be our first lecture, or our first official Physics 2 topics. We're going to be starting with collisions, momentum, and impulse. Okay, so what is momentum? Momentum is defined by this equation right here. It's P is equal to mv, where m is mass, v is velocity. So P is momentum. Okay. So what are the units for momentum? Well, it's simple. Let's just follow the logic. All right, we have P is equal to m, right? So m, the mass for the units for mass is kilograms. So kg times, and the units for velocity are meters per second. Meters per second. So of course, the units for momentum will be kilogram meter per second. Okay. So momentum is simply a property that objects that have mass have when they have a velocity. Okay. Now it's an important thing to know that momentum is independent to its directions. So what does this mean? It simply means that we have a momentum in the x-axis, and we can have momentum in the y-axis, and the momentum in the x-axis has nothing to do with the momentum in the y-axis. They are independent of each other. Alright, so we can see, for example, let's say someone throws a ball diagonally, right? Someone throws a ball diagonally. The ball has mass and it has a velocity, so it has some momentum here, and it's going to be its overall momentum. But this momentum can be split into its momentum horizontally and its momentum vertically. Does that make sense? And of course, your equations would look like this, right? You would have this is equal to mvx and mvy. This just simply means that the momentum horizontally only cares about the velocity that's horizontal, okay? And the momentum that's vertical only cares about its vertical velocity. Now, we can actually do some playing around with these equations. As you may know, Newton's second law tells us that F is equal to ma, right? Now, what I'm about to do is very important because it kind of solidifies the idea that physics builds upon itself. So whenever you see an equation like P is equal to mv or F is equal to ma, or whatever equation you see in physics, it does not come out of nowhere. There is always a process that gets you to that equation, and that's the process that we're about to do right now. So again, F is equal to ma. Now m is mass and a is acceleration. But what is acceleration? Well, we know what it is actually. We know that there's this equation right here. V is equal to v naught plus at. Right? Now let's say v naught is 0. Our initial velocity is 0, like an object is at rest. We have v is equal to at. Okay? And if we solve for a, we're going to have a is equal to v over t. More specifically, it's a is equal to change in v over change in t. Now, if you don't know what this symbol means, it just means it's called delta. It's a capital delta. It's a Greek letter, and it means change. So, for example, what you would do is change in v means your v final minus your v initial. Change in t would be t final minus t initial. Does that make sense? Now, why does this matter? Is because you may have heard of something that we call average velocity. So, for example, we say that velocity is equal to distance over time. But really, this is average velocity when this is delta x and delta t. But before we start, straying off on a tangent, let's get back to our equation. We have this right here, and we can plug this into this a right here. And what this gives us is f is going to be equal to m delta v over delta t. Okay? Now, if you're thinking critically here, you might notice that the top of this equation is momentum. It's momentum. The only difference is that this has a change in velocity, while our momentum up here only has one velocity value. It's not a change in velocity, right? And this is important because it actually leads to a very important concept of momentum, and that is that you can have a change in momentum. You can have, for example, my momentum can be 10 kilogram meters per second at one point, and then it can be 15. So then that means that there was a change in my momentum, and that change in momentum is what we call impulse. Okay, so again, let's stick to this equation, right? F is going to be equal to the change in momentum over change in time. Okay, and if we solve for this change in momentum, we're going to have change in p is equal to f delta t. Okay, and this is what we call impulse. Okay, so if we think about this equation right here, right? I said that impulse is a change in momentum, right? This is given by this. So then that means I can have one momentum one moment, and then this other moment I have a second momentum that's different from the first. So that means that impulse happened. A change in momentum happened. Now, if we study this equation, and I ask you what is impulse, you would say it is a force that is being applied over some period of time. Okay? But now we can actually come back and combine these two equations. Okay? And how? We can say, okay, if this is equal to this, and this is also equal to this, I can set impulse and change in p equal to each other. And that's exactly what we're going to do. Impulse is going to be equal to change in p. Okay? Now, what is changing p? Well, we know what p is, right? We know that p is equal to mv. So change in p has to be change in, or here, let's apply it like this. Change in mv, right? So change in m, change in v. However, this right here, where we are right now, does not make sense. And the reason for that is because there is no change in mass. Mass is a constant property that we apply to an object. If your mass is 100 kilograms on Earth, it'll be 100 kilograms on the moon. It'll be 100 kilograms everywhere. Okay. So now, that means that there is no change here, so this is going to be constant. So then at the end, we're left with this. Change in P is equal to M, change in V. And if we apply the concept that I wrote up here, we can say change in P is equal to M. If we, what I'm doing now is I'm substituting this into this. M is equal to V final minus V initial. Okay? And now if I expand it, change in P, it's going to be equal to M V final minus M V initial. And now just to finish off, we're going to put this back into this. And we will have impulse is going to be equal to the M V final minus M V initial. Okay? And this right here should show you how impulse is equal to the change in momentum. Okay? Now, the next topic is a very important topic. I will label it to emphasize the importance of it. Conservation of momentum. So what conservation of momentum says is that if I have some momentum here, I should have the same amount of momentum after. What goes in, goes out, even if it changes from one object to another. Okay? Now this is an important topic because now we're talking about not just one object's momentum. All of this was simply for one object, you know? But now we're talking about two different objects that can have two different masses and two different velocities. Alright, so the general equation for conservation of momentum is this. The momentum of one object plus the momentum of two objects has to equal the momentum of the first object changed plus the momentum of the second object changed. Okay? And if we expand that with our regular values, we know that mass is constant. So we're going to have M1 V1 plus M2 V2 is equal to M1 V1 prime. Okay, that's what this little tick means. It means prime as in modified or changed. Plus M2 V2 prime. Now this is an important notation because it shows you that change has occurred. And for us, it is especially important because we need to show that even though change has occurred, our equation still has the same value. Our conservation of momentum holds true. Now, I'll give you an example. Let's say I have a car A, right? Let's just say it's a toy car. It weighs 5 kilograms. Car B weighs 2 kilograms. And it's one of those wind-up cars that I can, pull back and then it'll start speeding through. So then for car A, its velocity is, let's just say 5 meters per second. And then for car 2, let's say it's 10 meters per second. Okay? Now, if I set up the cars so that they collide like this, right? So that this car is going this way, this car is going this way, right? Where this is car A and B. If I set these cars so that they collide, when they collide, right? They're going to do something that we call an inelastic collision. So what an inelastic collision means is that two objects are going to come together and they're going to stick together. Okay? And then once they stick together, they're going to move in one direction as one object, whether it be to the left or to the right. Okay? Now, we're going to apply these values up here, and we're going to figure out if our our combined cars are going to the left or to the right. Okay? So, we have 5 kilograms times 5 meters per second. This is the M1V1 part, plus 2 kilograms times 10 meters per second. Now, it's not just 10 meters per second. I said that car B is moving to the left. So this 10 meters per second is actually negative. And this is very important, because if we had said that it was positive, we're implying that both cars are moving to the right. And if that's the case, it is, depending on how we set up the cars would never touch. So then our problem falls apart. Okay, so it's very important to point that out. So now that we have this, right, we're going to say that this is equal to, let's just say this is equal to something over here, right? Let's just simplify the left side first. So here simply we have 25 kg per s plus 20 kg, or minus 20 kg meters per second. Okay, and we combine this, we're gonna end up with 5 kg meters per second. So we end up with a positive number, so we know that our momentum is to the right. So we know that the cars are going to stick together and they're going to move to the right. Okay? Now, what do we do about the right side? Okay? Up here, it says M1V1 and M2V2. But this is an inelastic collision. The objects are no longer separated after they collide. They are now one. So this is what we do. We say that there's a new car. We'll say that there's a new four-wheeled car that's equal to the mass of the two cars combined. And we'll call it M3. Where M3 is equal to M1 plus M2. And this new car, that's the combination of the two cars, has its own momentum. And that's the momentum that's at the end. Okay, so now we have this M3 with this new velocity prime, right? Now we know what the mass is of this car. It's simple. We just add up the mass of the two cars, right? So M1 is 5 kilograms and M2 is 2 kilograms. So together, it's 7 kilograms, right? So 5 kilograms meters per second is equal to 7 kilograms times this new velocity. Now, if our question is to find this new velocity, this is what we would do. Simply, we just divide by 7 kilograms. Okay? Divide by 7 kilograms. And at the end, we end up with our answer. Okay? We end up with our velocity being 0.71 meters per second to the right. So this means our conservation of momentum has occurred. Our momentum from the start, as we saw here, this is our momentum at the start, is going to equal our momentum at the end. And if we check, if we multiply this 0.71 meters per second times our 7 kilograms. It does give us back our 5 kilogram meters per second. So our conservation of momentum holds true. Our momentum was conserved. But in this type of collision, we just had the cars come together and stick together. Now there is one more type of collision, and it's what we'll end up on. Okay? It's called an elastic collision. So what is an elastic collision? Well, if an inelastic collision means that the objects come together and they stick together, an elastic means that they come together and they bounce apart. Okay, so we have car here, then they hit each other and then they bounce apart. And so this, they stick, and then this. Now let's say we stick with the same numbers from the first problem, except we're just gonna say that we know what the velocity of the first car is after it bounces apart. This is what's gonna happen. M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime. Now, we know what this left side is. We know that already that it's 5 kg ms. Now, I'm going to say that I know what the velocity of the first car is. After the collision occurs, I know that the car moves to the right with 1 meter per second. So I'm going to say V1 prime is equal to 1 meter per second, right, to the right. So then this means that this right here times 1 meter per second plus M2. Well, we know what M2 is. M2 is, if I check, 2 kilograms times the velocity, which we don't know, right? And now we can start solving this problem, okay? We can actually start seeing what our solution is. Per second. So this, when we subtract this from this, we actually end up with 0 over here. It's equal to 2 kg times V2 prime. And then obviously anything that we try to solve, we will end up with V2 prime is equal to 0. Okay? So what does this mean? It means that when the cars came together and they collided, they hit, and then one car was able to keep going, but the other car stood completely still. Okay? And that is an example of an elastic collision. We're now gonna head into the discussion portion of the class, and yeah, any questions, please feel free to ask them. I am here to help you.